So we generally think of space as a big place, but if you're launching a rocket from Earth, you're generally headed to one of two places, either low Earth orbit or geostationary orbit. Let me change this slide. So low Earth orbit is the region between 120 kilometers and 2,000 kilometers above Earth's surface. You can see that in this diagram right around here. Geostationary orbit is a very specific ring where satellites can orbit the Earth while remaining fixed above a point above the equator. That's seen right here. These orbits require little rocket fuel to reach, and because they are relatively close, satellites don't require much energy to transmit signals back down to Earth, making these orbits the perfect home for an incredible array of satellites, including the International Space Station. When a satellite stops working, another is launched to take its place, but the broken satellite doesn't leave orbit, quite the opposite, in fact. Today, operational satellites in low Earth orbit are far outnumbered by the graveyard of decommissioned satellites that will remain in orbit for hundreds of years to come. We call this population of defunct satellites space debris. So if you can imagine two satellites that collide in low Earth orbit, these satellites are orbiting at extremely high speed, 6 kilometers per second on average, meaning that when they collide, both satellites shatter into thousands of tiny pieces. Some of these pieces will fall back to Earth, but most of them will remain in orbit and become miniature pieces of space debris themselves. Donald J. Kessler was the first person to study this, and he found that while the chance of a collision between two pieces of debris is relatively small, when a collision does happen, the population of debris increases, which makes future collisions more likely. Over time, the number of objects in orbit increases, as well as the chance of collision between those objects. This effect is known as Kessler Syndrome. This graph just serves to illustrate that over the years, the number of objects in orbit has increased. Now the size makeup of space debris is very lopsided. When two satellites collide, you trade two pieces of large debris for thousands of tiny pieces of debris. And after many collisions, the small debris far outnumbers the large debris. This graph plots the flux of different sizes of debris. In this case, flux just means the number of things that pass through an area in a certain amount of time. I like to think of the following analogy. You can imagine a square cookie cutter that has a side length of 1 meter long. Now imagine someone throwing ping pong balls at that cookie cutter. If you were to count how many ping pong balls pass through this 1 meter long cookie cutter in a second, that is the flux of ping pong balls through the cookie cutter. You can kind of think of that. And in this case, we're just trading ping pong balls for pieces of space debris. We're counting the size of different objects and looking at their flux. This just tells us that you're far more likely to encounter a small object in low Earth orbit than a large object, because the flux is much higher. Now, as you can imagine, it isn't very good news when an active satellite collides with space debris. Luckily, as we've just seen, the chance of colliding with a large piece of debris is relatively low. However, even small debris can cause a lot of damage. So right here, you can see this crack right here is in the cupola module in the ISS, the International Space Station. That was caused by a tiny fleck of paint. It's like a millimeter long. Right here, this crack was caused is in the Challenger space probe. That was similarly caused by a very tiny piece of debris. So debris doesn't need to be very large to cause a lot of damage. Now, in order to mitigate the danger of space debris, there are several agencies around the globe who track the debris orbiting the Earth. Space Surveillance Network is one of them. They're run by the U.S. military, and they currently track around 8,000 objects. However, their radar sensors can't reliably find debris that is larger than 10 centimeters in diameter. As we've seen, debris smaller than 10 centimeters is still very dangerous. But the Space Surveillance Network is physically unable to warn the International Space Station or any other active satellite of the danger. Better detection techniques are needed. So in this project, I wanted to explore two such possible detection techniques and see whether or not it would be worth developing either of them any further. So before we talk about the first potential detection technique, let me give a bit of background. Light is a wave, and the energy of the wave is determined by the wavelength of the light. The different wavelengths of light form the electromagnetic spectrum. Now, all objects radiate energy in the form of light in the spectrum. Some of the light radiated by objects we can see, such as the light emitted by this piece of hot metal, but most of the light emitted we cannot, because the light emitted has too high a wavelength, or too long a wavelength, I should say. These objects still glow, however, and we can see the glow with special cameras, such as the thermal camera used to generate this image right here. The way that objects glow is called black body radiation. Now, the energy of the light emitted by a black body is determined by the temperature of the black body. As an object grows hotter, it emits higher energy light. This graph shows the black body radiation at different temperatures. The y-axis here is the amount of light emitted by different objects and at different temperatures, and this x-axis is the wavelength of the emitted light. As a black body gets hotter, the light it emits shifts to the shorter end of the spectrum, the shorter wavelengths. The range of the black body that the black body emits is called its emission spectra. I was curious whether it might be possible to identify pieces of debris in orbit using their emission spectra. So the most important question to ask here when wondering whether we can detect debris with emission spectra is, does the light emitted by the debris make it through the atmosphere? Because if it doesn't, then there's not anything that we can detect. Now, in order to know what the emission spectra of the space debris is, we need to know the temperature of the debris. This graph shows temperature as a function of distance from the sun, and we can see this distance at the Earth. We can see that at the distance of Earth, the temperature is roughly 0 degrees Celsius. Here's where this detection method falls flat. At a 0 degrees Celsius, most of the light emitted by the debris will be infrared, and that's absorbed by the atmosphere, which means none of it makes it to the surface. And this detection technique is completely fruitless. It won't do anything for us. So the second possible detection technique I wish to explore, it's a little more straightforward. Much of the debris in orbit around Earth is reflective, meaning that if the debris is pointing towards Earth, at night you may be able to see a glint of sunlight reflected off the debris. If the amount of reflected light is greater than the background light that we would observe anyways from stars, then we might be able to use the reflected light from debris to find the debris. Yeah, so it seems like a long shot if we're talking about a single piece of tiny debris orbiting the Earth, but if we were to imagine a cloud of debris orbiting together, then it becomes a little more plausible. The question we need to answer in this case then is, what size of a cloud of debris would we need in order to see it? So in order to test the plausibility of this technique, we came up with a very simple model of our debris scenario. We first assumed the debris reflects all the sunlight it touches, which is really optimistic, but it makes the calculations easier. Then we assumed that the light reflected from the debris would spread out equally in all directions. This model basically just treats the debris as little light bulbs glowing with the same brightness as the sun. Then our question will be answered when we can find out how many of these light bulbs we need to see them over the night stars. Okay, so I wanted to show this process a little bit, but I'm running out of time, so I'm going to give you the Cliff Note version. So I was going to discuss the process, but I'll give you the Cliff Note. Remember the concept of flux from a few slides back? Here I wanted to compare the flux of light from the reflected debris, the flux from reflected debris to the background flux of the stars. So this number right here that we obtained, skipping all this is the background flux, and we just want the reflected flux to be greater than this quantity. Over here, this is the reflected flux at a distance d, which is just the distance from us to the debris. And this right here is the variable we will be solving for. That's the total area of the debris that we will need to see it. In this next slide, we just compare these two with an inequality. So we want the light flux of the reflected light flux to be greater than the background flux. Solving for these and plugging in a distance of 200 kilometers, which is just the lower bound of LowEarth Orbit, we obtain this value for our area, which just means that in order to be able to see the debris over the background flux, we would need to have a combined reflective area of 7,872 meters squared, which... So, with that in mind, is this a feasible detection method? Well, 7,800 meters squared is a lot of surface area. It's a bit bigger than the surface area of an entire American football field, to give you an idea. If we imagine that the area forms a square, then the square would need to have a length of 88.7 meters to make up that total area. However, if you point a telescope at the night sky, you're looking at a tremendously large area of the sky, much bigger than just a football field. What our estimation tells us is that in low Earth orbit, we might be able to detect space debris with the sunlight that reflects off of it. We just need to be able to have it. We just need a big enough cloud. So the only way to know for sure whether this technique would work would be to develop more rigorous mathematical models and go out and actually test it. So space is a big place, but as we move farther into the age of space exploration, Earth's orbital space grows smaller and smaller. Space debris poses a looming risk to satellites in orbit, the satellites we rely on for GPS navigation, satellite TV, and cell phone communication, and it poses an even greater risk to astronauts aboard the ISS. This picture shows the view from the cupola module, and to save it from further potentially catastrophic collisions, we need to develop better techniques to detect debris from Earth orbit. Whether it be reflectivity or some other novel technique, it is paramount that we open our eyes to the invisible junk circling our planet so that we can preserve both our current ability to live and operate in space and promote future advancements as we press forward into the final frontier. Thank you for your time. Are there any questions? No? Yes. Yes, actually, if I can go back to the first slide over here. In this graph right here, you can see it kind of tells you, right here, this was a collision with two satellites. Iridium was an American satellite. It collided with, I guess that would be the Cosmos. That was a Russian satellite. So those are two communication satellites that were in use. They were active, and they collided, and they aren't here anymore. That happened in 2009, so. Yeah. Yeah, so I don't have the timelines for those. I don't know that. That one was significant because there was two active satellites, but before that time there were a lot of instances where active satellites were put out of commission by space debris that we didn't see coming. It just, one day the satellite was there and the next it was gone. Well, thank you. Any others? Great. Thank you very much.